Hey there, this is Qasim Wani and welcome to another reinforcement learning video. In this video, we'll continue on the previous discussion on the prioritized experience replays and more specifically dive into the paper that DeepMind published on their approaches towards building a more robust experience replay buffer and the techniques surrounding that in 2016. So without further ado, let's get into it. If you haven't watched my previous video on this, I highly suggest you do watch it. It sort of builds up to this moment of the motivation behind using an experience replay in the first place and the fallbacks with it and how to combat those using the prioritized experience replay. So just to recap, the idea behind using experience replay helps the agent in reusing experiences from the past instead of, especially for on-policy methods such as the Q-learning, SARSA, instead of just replaying an episode one time and letting go forever. Using experience replay lets you replay episodes at random, but there's potential fallbacks with it. As you can see, just from the highlighted stuff over here, a uniform sample from a replay memory can, at the same frequency, has pitfalls, and that's what we'll cover in this video. Let's read through sort of some of the highlighted stuff that I have and sort of talk more about this paper in general. So this paper introduces the motivation behind using experience replay in the first place, and that is essentially the motivation is to discard is from the fact that when you're using, in its simplest form, an on-policy method discards incoming information immediately after a single update and and uses that to build up on the Q table to learn from it. And there's two problems with it. The first, as you can see, is that there's strong correlated updates between immediate state action pairs, and we talked about this in the previous video. And to break that up, you build up this relay or this buffer that samples at IID from it through a mini batch for your deep Q network using a stochastic gradient based algorithm. The second is the problem with, in general, the experience buffer or the traditional Q learning approach is that you forget, there's a rapid forgetting of the rare experiences that would be useful later on. So every episode has an equal priority, and so you're risking not being able to resample from experiences that are more important, and they would be considered at equals with experiences that are less important. So that's the idea behind it, and sort of for point number one, which is the strongly correlated updates, this would break up the temporal correlation by using a buffer. And in the paper, they mentioned this as a sliding window replay memory. And the problem is, the problem with this is how do you prioritize which transitions are replayed, and that can make a significant improvement in faster conversions towards the optimal policy. And that's exactly what the paper strives for, is to how can an agent learn more efficiently from some transitions than others. And this is sort of the thesis behind this paper is in the following two sentences, where I'm just going to read it verbatim, that experience replay liberates online learning agents from processing transitions in the exact order they're experienced. Prioritized replay further liberates agents from considering transitions with the same frequency that they're experienced. In particular, we propose to more frequently replay transitions with high expected learning progress as measuring by the magnitude of their TD error. And so this sort of is the way how they sort of go from the regular experience replays to building this prioritized approach. And the way they do it is by tapping into the ability of your TD error score from the tuple of the state in action when you're sampling. Your agent, goes into the environment and collects an action and gets the result from it, right? And the way you do that is by looking at the the error between. Let's see, I'm trying to find the formula. Should be up here somewhere. The idea is to minimize the error between the model Q table and the TD target, right? And the way you do that is because every time you do sample, you're getting the current TD target, and you're also have, based on your previous build, you have the entire network. And essentially, that's the goal, is to perform stochastic gradient descent on those two batches and minimize it. But using the share, just the magnitude of it between the TD target and the model, the main model, you have the ability to provide with a priority for each experience. And the background, or sort of the rationale behind it, is based on neuroscience and how and how the hippocampus of rodents use previous experiences or use sequences associated with rewards that appear more frequently or replayed over and over again than experiences with smaller rewards. And so this suggests that experiences with high magnitude of TD error can be also, or should be, replayed more often than other experiences. And so this background from neuroscience sort of aids or goes away from the null hypothesis, which is that there now could be more evidence of using this approximation or using a priority to provide a better model. And you can actually see this from this graph over here. And what this graph basically suggests or demonstrates is the fact that there was a study by the DeepMind team conducted regarding the blind cliff walk environment, right? And essentially the goal is to go from point A to point B without falling off the cliff. And when you're sampling every episode, every sequence experience from random, you can see that as the number of samples increases, the update required on the update on the Q table on your learning algorithm increases exponentially. And so you can look at it from this log scale, and a linear line indicates an exponential behavior, right? And so what this also suggests that it takes longer time to converge to the optimal policy. And this polynomial scale can be a huge burden on your training networks, because now you now have this sort of the very baseline that now the agent is going to perform is going to learn at polynomial times, right? And that can be really hard towards coming towards the optimal policy, because now you will just take a lot of time. But now when you introduce this oracle, right, so this external environment which sort of pushes you towards, or which gives you this added hints towards how to approach towards the optimal policy, you can see that the gap between the Oracle use approach and the standard experience buffer replay use approach is quite significant. And this is a motivating factor behind something that should exist in the middle towards estimating a better policy, right? And that's where they use the prioritization method. And the way to do that is essentially taking the error, right? So the magnitude of a transition's TD error, which they call delta, and the larger the error, the more unexpected the next state given the previous action from the previous state, right? And this is quite useful because now you have this indication of how well your model is behaving, but at the same time, you now have an indication of where to improve based on what sample of action that you've just taken given its current state. Now, the only sort of the caveat towards this is that this sort of TDR approach can be a poor estimate in circumstances when the rewards are noisy. And so there's like other approaches for it, which we won't get into this video. And so this is a very, so that's the motivation, right? How do you reduce the gap between the agent that performs using the Oracle as its policy versus a uniform sort of mini batches and using each sample at random with IID. And to sort of, you know, the stack behind this, right, is a priority queue, and with certain updates to it that you have the ability to update and fetch. And we know, you know, just data structures 101, for like fetching an element from finding the element of maximum priority is at the top, and that is order of 1, it's constant time, versus updating priorities is order of log n, right? So it's O log n. And the way sort of you do it is by using this idea of a stochastic prioritization, right? And this idea of finding out the TD error, so the delta or the gamma, essentially, sorry, the delta between the TD target and the model itself, and use that delta as its rough score, priority score, and the way you define its probability of being sampled at a transition, I can be given through this formula here, where its priority is divided by the total cumulative value of all the priorities. And this is guaranteed to give you a stochastic measure. Now, the problem with this approach is using just P of I and dividing by the sum, discarding the alpha, is that when you're using this, you are eliminating the idea of an IID distribution. You're eliminating the idea of sampling at random. You're introducing now a system that is very prone to overfitting, because now you're sampling from, you're always going to sample from frequencies that are very high in nature, meaning they have a much higher priority, and you're never going to learn from less samples or experiences with smaller TD errors. And this is obviously going to introduce overfitting in your model. And the way you sort of fix this is, instead of going from this pure greedy prioritization, you sort of introduce this hyperparameter alpha, which can fluctuate between a uniform transition to a very greedy prioritization, right? And that is exactly what they talk about here, where it literally says that the alpha determines how much prioritization is used, with alpha equals 0 corresponding to the uniform case. And so that's like the general idea behind this. And this is sort of like the bulk, which is the actual algorithm behind it. And it's very intuitive. It makes sense, right? So what you do is you basically initialize all your variables, and we're not going to get into that, But if you look at it, when you are sampling, right, when you are storing values into your buffer, and this will be a deck, so a double-ended queue, because it has to be a circular array or circular stack of the fixed size, right? And you're taking out the state, action, immediate reward, and then the delta or the priority, and the next state. And what you're doing is when you are transitioning, right, you compute the weight. And I guess before we talk about that, we should mention, I guess it's, yeah, so we'll talk about, let me just talk about this briefly and I'll go into more details about this. What you're going to do is you're going to introduce something called an importance sampling weight. And you're going to use this sort of, this is like the formula for it. And you're going to use this for computing the TD error, which would be used in the update rule for your gradient descent, right? For accumulating for the weight change through your stochastic gradient descent. And you're gonna obviously, so this would be through your, it could be, if it's a video-based solution or video-based agent, you would have multiple convolutional layers with like max pooling, dropout, filters, and etc. But if it's just a very regular sort of state value that you're getting instead of pixel value, it could be multiple dense layers, sort of the regular artificial neural network example scheme, right? And you're basically updating your parameters W with respect to the weight, right? So the gradient is based on the weight itself, theta or W. And essentially, that's kind of what it does is basically once you're updating it, after several updates, you're going to update the target, but the main model gets updated every single time. And the reason why you have firstly two different models is because you don't want to, you want to prevent yourself from the exploding gradient or the vanishing gradient problem, and also because because of the fact that your model will not be able to converge at all or properly if the target is equivalent to the weight at every single iteration. If you didn't understand what that means, watch my video, not the previous one, but the one before that in the series on double, I believe it's double Q learning. And that talks about why you need to have the one main model in a target network and update the main model every single iteration, and target network after several iterations, and then combine them together, coalesce them together. And so that sort of explains it, the rationale behind this approach that we have over here. And I'll link the video to that in the description below. So I mentioned the need of, or I just mentioned, alluded to using a sampling weight. And the reason behind using this is because of the fact that in general, the prioritized replay creates this bias that is done through the fact that experiences of higher priority will be sampled first, regardless of sort of, they will always be guaranteed a sample first, and gets rid of the IID distribution, which is key to the whole MDP process. And you correct this by introducing an importance sampling weight, which is given by this equation over here. And what it does is basically it compensates for the sort of the non-uniform probabilities, such that experiences that are of high priority can also are biased more, such that experiences with lower priorities are sampled can be sampled at random and have an equal chance as experiences with higher priorities, right? And so the way you essentially tune it is by introducing another hyperparameter beta, such that if beta equals 1, now you're just filling it at a non-uniform probability. As you can see over here, it's just 1 over the total number of samples divided by the probability, the priority of that, right? And so that just takes apart the idea of it all. And if you want to know why this is the case, is because if we go all the way up So you have this, right? 1 over this times this would essentially just give you 1 over n, right? So if this is equal to p over I, and you're multiplying that by the target, by the delta itself, the priority itself, that would essentially equate to 1 over n, since these two terms would cancel out. And so now each one can be sampled at random. And you want to go from at random to greedy policy, greedy method. And the way you go from this to this is by using the sort of hyperparameter beta. And so that's the idea behind using the stochastic prioritization induced with this important sampling method. And in this part of the paper, it sort of briefly mentions or talks about the 50, around, I believe 57 games, and the gap between random and human, and also using rank-based approach and proportional approach. And that's sort of the gist behind the remainder of the paper. I just wanted to talk about sort of the conclusion. Now we're going towards the end of the video. The idea, sort of the comparison that we led from rank-based variance or variant to is the fact that to the proportional prioritization is that the rank base, which we just talked about, is more robust because it is not, as mentioned in the paper, literally is not mentioned by the outliers or its error magnitudes. And this can lead to more diverse training sets and can lead to better results that are less prone from overfitting early on. And so this whole idea of using prioritized experience replays goes into other areas as well. So it's not strictly RL focused. And one example of this is in supervised learning. So in this, the authors talked about the classical MNIST data digit classification, where you're given digits from 0 to 9, and your goal is to build a neural network or a classifier that can classify between these digits. And what they did was they intentionally reduced the training size of digits 0 through 4 by 99%, and they left its corresponding test or validation sets as is. So now it had less data for digits 0 through 4, but the same amount of data for the remaining digits. Now, just a classical and neural network, when trained on this, would be more biased towards elements 0 through 4, and because it won't be able to learn a better function approximation. But using the approaches that we just discussed of the prioritized experiences, what it does is when it samples by priority, it outperformed the uniform-based distribution or the uniform baseline, and was able to be a better indicator and sort of the based on its approaches and the performance in terms of the generalization that it gained from the value of the function approximation, which led to a better classification result. And I guess that sort of concludes this video. At the end, I would say they found that, I guess, the speeds, it's much faster, it converges much faster. In fact, when trained on Atari, benchmark was able to converge by a factor of 2, and unlike the traditional experience replay-based buffers. So that sort of covers this paper, this video as well. If you enjoyed it, do support it in your peculiar ways. And yeah, I guess hopefully you understood a bit more on what the contributions that this paper has had with its novel approach towards going away from the experience replay and its fallbacks towards more robust approach towards building a better algorithm that can converge more optimally towards the optimal policy pi star. Yeah, so thank you and good day.